Okay, so let us start. So what we did last time is we talked about error analysis, right? So we spoke about the error in computation of the solution of the system of linear equations by using an iterative method. And then we see the error bound by using the norm of the matrix, iterative matrix, and the distance between the two successive solutions, right? So successive approximation. Right? So now what we are going to do is we are going to talk about the error in terms of general solution, right? So now right, so this chapter or this section is called errors and residuals, right? So this here what we are going to do is we are going to talk about the error in terms of general concept, right? So this is the first thing, right? So we are okay. So when we do a numerical computation, right? So we will ended up with a computed solution, and then we take that computed solution as the approximation for the real solution x. That is what we do in first chapter as well as the second chapter, right? In first chapter we use elimination methods to get the approximation, right? In chapter 2 we do iterative methods to get the approximation, right? So here what we do is in both cases basically the real solution is approximated by the computed solution. So obviously the difference between the real solution and the computed solution is known as the error, right? So error is x minus x hat. So x hat is the computed solution. But obviously you know that you cannot compute the error, right? Because you don't know, honestly, in a numerical problem you don't know the real answer, right? So you only have the approximation. So basically you cannot compute the error. So we look for something else which can be computable, right? Which in a way can interpret the error. So for that, we define some concept called residual. Residual is the right hand side vector b minus ax when x is replaced by the computed solution. So this is the original right hand side vector and this is the computed right hand side vector. So the difference between the real right hand side vector and the computed right hand side vector. Give me a minute. Hello. എന്നെയും വരച്ചല്ലേ എന്നെയും വരച്ചു ആ ആ ആ ഇപ്പൊ ഇമെയിലും போட்டுருக்கே சரி சரியா எனக்கு ஃபோன் பண்ணி சொன்னே வேற அதுதான் அது இப்படி முடியலாது இன்றைக்கு நானும் சொன்னேன் இப்போ வகுப்பு இருக்கு நான் வகுப்புல நிற்கிறேன் அப்ப நான் எல்லாம் 3 வயசு நான் 3 வயசு தான் வருவேன் வந்துட்டு நான் உடனே போயிடுவேன் பேட்ச் நிற்க மாட்டேன் ஓ அதான் அதான் ஓ அப்படித்தான் நானும் சொல்ல போறேன் இன்னைக்கு நான் சொல்லிவிட்டு நான் உடனே எழுப்பி வந்துடுறேன் நிற்க மாட்டேன் அதுக்கு சரி அது அப்படிதான் சொல்ல போறேன் 3 வயசு தான் சரி. Okay, so we have something which is computable, right? So you notice that R can be computable, right? So observation is R is computable. Right? So R is computable. So you can always try to compute the R, and R, this residual, can serve as a approximation for the error, right? So this can be also considered as an error, and you can intuitively see that if you reduce the R, right, basically if the approximation is ideal, right, then R should be 0, right? So you notice that also. Right, so obviously if R is equal to 0, then x hat is a real solution, right? So that is the case here, right? So the idea of reducing the error now is into the case of reducing the residual, right? So this kind of interpretation leads to something called iterative improvement, right? So right, so this leads to something called iterative improvement, right? So first of all, you note that right, first of all, from this you can notice that this is basically a times x minus x hat, so basically a times e, right? So you can easily see that R is equal to a times e, right? So the difference between x and x hat is error, so R can be considered as a times e is equal to R. So this is a new system of linear equation, right? So you can always compute R here, right? Right, so where R is hat, right? So you notice that this is again a system of linear equation, right? Okay, so here you can always solve this system AE is equal to R because you know A and you know R. So you can solve the system AE is equal to R. Again, when you solve the system, you don't get the exact answer. So you get an approximation. So by solving the system, either by LU factorization or whatever the factorization you studied in the first chapter, or by iterative method which you study in the second chapter, right? By using any of those methods, you can find an approximation E naught for this system, the solution of this system, right? So E naught, now you know, is an approximation for the error, right? So clearly E naught is an approximation for the error. Right? So then after getting this E naught, which is the approximation, right? So you update X hat by adding E naught to that, right? So that is X1 is equal to X hat plus E1. So you find a new vector called X1. So obviously that is going to be a much better approximation to X, right? Right, so obviously X1 turned out to be a better approximation for X, right? So obviously if that is a better approximation, right, then you improve the solution, right? So what you do is you start with an initial approximation X hat, and then you solve the system A is equal to R, and then you improve the system. So improve the solution, right? Now, if you continue doing this again and again and again, you will get a sequence of improved solutions, right? That leads to the better or best approximation for the real solution, right? So that is how we are going to define the iterative improvement, right? So I'm going to define it in a formal way now. Right, so the step one is you have X naught as the initial approximation for the real solution X, right? So then what you do is, okay, is equal to, right? So what you do is, you start with an initial value x naught, right? And then what you do is, you start finding R1, which is b minus ax naught, and then you solve the system AE is equal to R1, right, to get E1, right, and then you get x1 is x naught plus E1, and then you repeat, right? So putting x1, you get R2, right, and then you get E2, then x3 is equal to x2 plus E2, right? So in this way you keep on computing again and again and again, right? Right, so this stops when norm of Rk gets almost equal to 0, right? So you can set the tolerance as small as possible, right? And then you can get the iteration stop for when the Rk, norm of Rk falls below the tolerance, right? So that is how you can do the iterative improvement, right? So once you have this iterative improvement, right, we are going to see certain error bounds, right? So what we are going to do is to first we are going to see the residual bound, right? So now you see that R is the residual, and you can use that as a replacement for the error, right? So and your goal is to reduce the error, right? So we are going to see, or we are going to define an error bound for the residual. Okay, so I'm going to define residual bound. First, so in order to define the residual, let us define first a concept called condition number, right? So this is just a notation basically, right? So this notation is not denoted by C of A, right? which is the norm of A times norm of A infinity. We call this as condition number, right? So this has something to do with the condition of the system, right? So we will talk about what do we mean by condition of the system later sometime, right? So that is how we define condition number. Right? So based on that, we are going to define the following residual theorem. Right? So I'm going to write this as a theorem. So let us say y be the computed solution of the system Ax equal to b, right? Then we have this. The first one is norm of E is less or equal to norm of A inverse times norm of R, right? Second one is the error bound. So 1 upon condition number of A times okay. So now this theorem tells you why reducing the residual will reduce the error as well, right? Because you know that this term is the relative error or in the approximation, right? So E is the error, X is the real solution. So E divided by X, norm of E divided by norm of X is the relative error, right? So we see that the relative error is bounded by a ratio of residual, right, on the or bounded by a ratio of residual above and below, right? At the same time, error is also bounded by above by another constant multiple of residual, right? So now by equation 1 and relation 1 and relation 2, you can see that you can always reduce the residual to reduce the error, right? So if you want to reduce the error, you just need to reduce the residual, right? So that is why it is called residual theorem. So now let us prove this. The proofs are not that hard, right? So they are just straightforward computations. Right, so first thing, I wrote this earlier also, R residual is B minus AX hat. So here they say Y is the computed solution, so you use Y. Right, so, and then that is basically AE, right? So then from this you know that E is equal to A inverse R. Right? So A inverse R. So if you take the norm, that is clear that norm of E is norm of A inverse R by using the norm property, that is norm of A inverse times norm of R. So that first part is clear from this. Right? So now you need to do the second part. Right? So second part we will do in two pieces. Right? we will show the upper bound separately and we will show the lower bound separately. Right? So to show the upper bound, this is what we do. Right? So you know that norm of E over norm of X is what you want to get. That is basically less or equal to norm of A inverse times norm of R over norm of X. Right? So that is this. But you know E is less or equal to A inverse R, so you substitute it. But what you want to get is C of A times R over B, right? But C of A is A times A inverse. So you have to bring some A here, right? So if you want to bring this A here, and remember this is less or equal. So this is basically equal to norm of A times norm of A inverse times norm of R over norm of A times norm of X. Right, so you multiply and divide by norm of A on the top and bottom. So this is basically C of A times norm of R over norm of A times X. But AX is equal to B, right? So that is obvious for you. AX equal to B. So norm of B is less or equal to norm of A times norm of X. So 1 upon norm of B is greater or equal to 1 upon norm of A times norm of X, right? So this is just a simple mathematics, right? So AX equal to B, when you take the norm, you get norm of B is less or equal to norm of A times norm of X. So 1 upon B is greater or equal to 1 upon A times 1 upon X. So this is basically less or equal to C of A times norm of R over norm of B. Right, so you take this and apply here. Right, so that is how you get the first relationship. E of E over X is less or equal to C of A times R over B. Right. Now the other inequality. Okay, so for the other inequality, you want to get this, right? So first, R is equal to AE. So from this, you get norm of R is less or equal to norm of A times norm of E, right? So basically, norm of E over norm of X is greater or equal to, right? E is greater or equal to A upon R upon A, R upon norm of A times norm of X. Right? But X is A inverse B, right? So this you have, right? But AX equal to B, right? So norm of B is less or equal to norm of A inverse, sorry, norm of X is less or equal to norm of A inverse norm of B, right? Norm of X is equal to, right, because from this you know X is equal to A inverse B, right? So norm of X is less or equal to norm of A inverse B. So 1 upon norm of X is greater or equal to 1 upon norm of A inverse times norm of B, right? So you take this and put it here, right? So if you take this and put it here, you get this is greater or equal to norm of R over, there is a norm of A, right? And then 1 upon X is greater or equal to A inverse times B. right? So this is basically 1 upon condition number of A, right, times norm of R over norm of B. Right? So that gives you the other inequality. Right? So so now you completed both the inequalities, right? So you have E over X is less or equal to CA times R over B. There you have E over X is greater than or equal to 1 upon CA over CA times R over B. So in both cases, you have the proven the bound, upper bound and lower bound for the relative error in terms of condition number and the residual. Right? So I will write this as a remark here. Right? So 1 and 2, basically 1 gives you the error bound for the error, upper bound for the error. 2 gives you an upper bound and lower bound for the relative error in terms of the real solution. Right? So in terms of the residual. Right? So that is what we prove in this part. Now what we are going to do is we are going to see another kind of error. Right? So here it is the error which is obtained by using the computed solution as the approximation for the real solution, right? So in both the cases, the last class also, this class also, what we did is we take the computed solution as an approximation for the real solution. Right? However, there is another way that error can be appear, right? So there will be another reason for error to be included in the real solution, right? So that reason is the input errors, right? So you know that when you are doing a computation, you use the matrix A and B as the given values or given components, and then you compute X, be it a elimination method or be it an iterative method. In both cases, say if you are doing a computer program, right, your inputs are A and B, right, and your output is going to be X. So there is a possibility that there might be some errors in the input, right? Either by a human mistake, right? So when you are entering a value, you might have made a mistake, or by the nature of the computer, right? So the way the number of digits can be handled, right? So that also causes an input error. So in that case also, you can expect a difference in the computed solution from the real solution. So those kind of errors are called perturbation errors. Right? So now what we are going to do is we are going to see how perturbation error comes, and we try to develop a perturbation error bound. Right? Right, so this is called perturbation error. Right, so this is called perturbation error. Okay, so let's see. Right, so there might be errors in the input A and B. So we call those errors as perturbation, right? So that is right. So this is, that means A is inputted as A plus delta A, and then the input for B is B plus delta B. So there is a slight small deviation in the input, right? So there's a small deviation in A as well as there is a small deviation in B. So in that case, we shall try to develop an error bound for these deviations. Right, so that is what we are going to do here. We will try to develop an error bound in the solution. Right, so in such case, there may be right. So if x hat is the computed solution, we can say that it is a delta x away from the real solution, right? So if x is the real solution, the computed solution is a delta x away from x. Whenever there is a and b are a delta a and delta b away from the real solution, right? So we shall try to develop the error bound, right? So perturbation bound. So in order to do that, we need the following results, right? So we have to have the following results. Okay, so I will write the lemma first. right? So you don't need, you can just say just an in norm. That's enough. If norm of A is less than 1, then I minus A is non-singular. That is the first results. Second results is this. Third one is this. Right? So okay, so these are the results we have. Right, so if A, norm of A is less than 1, then I minus A is non-singular, right? And then this I minus A limit is in this, and then this one is true, right? So I leave this proof as an exercise, right? So you can read this, or maybe I can say if row of A is less than 1 and norm of A, so then that is easier, right? If row of A is less than 1 and norm of A is also less than 1, then you can easily prove these three results, right? So this is available in all the numerical analysis textbooks, right? So our matrix computation textbooks, right? So you can easily read them and see the proofs. So I am leaving these proofs as an exercise for you to refer in textbooks and try to see how to prove these results, right? By using these, I am going to prove the error bound, the perturbation error bound. Okay, so this is the error bound. I am going to write it as a theorem. Okay, so the perturbation error bound for this problem Ax equal to B, when we have the perturbation delta A and delta B in the input values A and B, right? Let y be the computed solution with the perturbations. So basically y is equal to x plus delta x. And so in that case, you see that y minus x over x, that is the relative error, right? Is, sorry, not equal. This has to be less or equal. Right, is bounded above by this value, right? So C of A over 1 minus C of A times delta A over A times delta A over A plus delta B over B. Right, so you can see that everything on the right hand side is a known value, right? So you bound the perturbation error by using the perturbations in A and B, right? So we shall prove this, right? So in order to prove this, let me take this way, right? So let y is equal to x plus delta x. So you have A plus delta A times x plus delta x is equal to b plus delta b, right? So you simplify this, right? So what you do is A plus delta AX right? So you keep delta x on one side and move everything else to the other side, right? So that's the first step you do. And then you notice that this and this are same, right? So that is the first thing, right? Oh, sorry, there's a mistake here. I have to make this as delta A, right? So A be the perturbation, and that should satisfy A inverse delta A is less than 1. So you know that if in the theorem you have A inverse delta A, but you have a delta A, so you have to bring A inverse here. So what I do is I am going to factor it out. Right? So here if I take A out, I will have I plus A inverse delta A times delta X is equal to, I have delta B minus delta A times X. Right? So basically I have this delta X is less or equal to I plus A inverse delta A quantity inverse times A inverse, right, times delta B plus delta A times norm of X. Right, so I have this. I take delta A here and move all these to the other side, and I take the norm and apply norm inequality, right? So I do several things in this here. So by doing this, what I did is I have delta X is less or equal to I plus A inverse delta A inverse times A inverse times delta B, and when you take the norm, minus become plus, and less than delta A plus delta A times delta X, right? So you have this, right? But you know that I plus A inverse delta A quantity inverse is less or equal to 1 over 1 minus norm of A inverse delta A, right? So that is according to the lemma, right? Because this norm is less than 1, according to the lemma, right, I have this, right, this by lemma. And so this is by lemma. And then I use the norm relationship again, right? So this is less or equal to 1 over 1 minus norm of A inverse times norm of delta A. So that is basically 1 over 1 minus A inverse times A times delta A over norm of A. Right, so because you know that you should have some CA here, so you have A inverse, so you multiply and divide by A. So eventually what you get is this is equal to 1 over 1 minus C of A times delta A over norm of A. Right, so for this part you have this relationship, right? So but you want to get a CA here, so you have an A inverse here. So if you put A, you divide by A. Okay, so what you do is, now you have delta X less or equal to A inverse times you put an A, right, over 1 minus C of A times delta A over norm of A, right? Because you put an extra A here, you divide by A, right? So you have delta B over delta A plus delta A norm of X over norm of A, right? So you have this. You have an X here, you want to divide by this X. So basically when you divide, you get delta X over norm of X is less or equal to, this is C of A over 1 minus C of A times norm of delta A over norm of A times this one, you have delta B over norm of A times norm of X, because you have to factor out an X from there. So because you don't have an X here, you divide by X, and this is delta A over A. So you are almost closed except this part. This you should have B here, right? So but again, you know B is equal to AX. So norm of B is less or equal to norm of A times norm of X. So 1 upon norm of B is greater or equal to 1 upon norm of A times norm of X. Right? So now if you take this and substitute here, you will get the required results. Right? So if you substitute here, you get this. And you substitute here, you get delta X over norm of X is less or equal to C of A over 1 minus C of A times norm of A, sorry, delta A over norm of A times norm of delta B over B plus norm of delta A over norm of A. Okay, so this is what you are asked to prove, right? So the perturbation error bound. So in this case, you use the previous lemma here, and then all the other places you use the norm property, right? So by using the norm property, using the fact that A is equal to B, and also using the fact that A inverse, norm of A inverse times norm of A is equal to CA, the condition number of A, you are able to derive the upper bound for the relative error, relative perturbation error, right? So this is Right, so this is basically an upper bound for the relative error, right? Because delta x is the error, divided by x is the relative error. So this is an upper bound for the relative error caused by the perturbation in A and delta A, right? So in A and B, right? So that is how you get the error bound for the perturbation. So this is more or less what you need to learn on error analysis, because there are two ways that numerical error can be acquired. One is by the nature of approximation, right? Because you approximate the solution at some point by a certain approximation. So because of that, there is an error. So in those cases, you can estimate the error by certain upper bounds, right? So, and then we see residual is an alternative way of approximating the errors. And then the other type of error is called perturbation error, that is obtained by certain perturbations in the input values. So for that also we derive a bound, or we estimate the error by a certain perturbation bound, right? So this is all about errors and the bounds in the solution of the system of linear equation, right? So that concludes chapter 2 here, right? And then we are going to start chapter 3 next. In chapter 3, what we are going to do is we are going to talk about some other properties of a matrix, right? So far we talk about system of linear equation, chapter 1 and chapter 2. We talked about system of linear equation. In chapter 3, we will only consider a matrix, right? A matrix A, and then there we will try to find the eigenvalues of that matrix, right? So that is the purpose, or that is the aim we are going to have in chapter 3. We are going to see how we can find the eigenvalues of the given matrix, right? So that will be done in next Monday class. So Monday we will start chapter 3 with eigenvalues, how to compute the eigenvalues, right? So I will stop here and then continue on Monday.